Hello everyone, I'm Norman Wildberger. We're talking about the algebraic calculus and the geometry of de Casteljau Bezier curves. Today we're going to look at de Casteljau's algorithm and splitting dCB curves. We're going back to an essential technology introduced by Paul de Casteljau during the very early days of this subject. In the early 60s, he and Pierre Bezier revolutionized this aspect of algebraic geometry and sort of introduced this whole new approach to algebraic geometry centered on these parametrizable curves that ended up being so important in industrial applications these days, animations, robotics, all kinds of industrial applications. This algorithm they're going to tell you about today is really at the heart of the theoretical understanding of these things. So to do this, I'm going to look at a very specific curve. So we looked at some general ones. I want to actually sort of pin down a particular one that we can sort of become familiar with and look at in some detail. So I'm going to choose some particular control points, these ones right here. P0, the 0th one will be at the origin, 0, 0, and then P1 will be at 1, 2, P2 will be at the point 3, 3, P3 will be at point 4, minus 1, and P4 at the point 6, 1. So it's 5 control points. That means this is a quartic curve. There it is there. And here are these various intermediate points that are constructed that I explained to you last time. I hope you've absorbed that. And ultimately, the curve is the locus of this point T0, which is sort of the culmination of all these constructions. As our parameter T varies, this point T0 marches from P0 up to P4. So we're going to look at this more carefully today. All right, so here's the same data now in a GeoGebra worksheet, and you can see everything laid out here on the left-hand side. You see all the points, the control points, P0 to P4 in blue, and then the red ones, the Q0, Q1, Q2, Q3, and then the next level, the green R points, and then the purple S points, and finally down here, the T0 point. And here's our parameter, which we can actually slide around, and as we slide this around, we can see how everything moves and how this T0 forms the curve that we're interested in. Okay, so this is quite an interesting thing that we sort of have this layering of information. So at the bottom, you might say, are the control points themselves, and then we have these sort of secondary and third level and so on, points, so sort of interpolating things. But in some sense, it's all very discrete, right? That's why this is so ideally suited for industrial applications and robotics and so on, because you can control a seemingly continuous object with just a discrete amount of information. So today we want to investigate this de Casteljau algorithm, which will clarify the nature and the role of these intermediate points and what they're useful for. And we're particularly interested, say, in this segment here, which we can see is tangent to the curve, the segment S0, S1, on which T0 is lying. That is always tangent to the curve, which is a very interesting thing. And we're going to be talking also about splitting the de Casteljau Bezier curve. So for example, suppose we right at this stage here, we want to split it. Let me get it down back to 0.4. Okay, so there's the t value of 0.4. If we wanted to split the curve right there, cut it into two pieces, then there would be this part there and then this part there. And a natural question is, how do you describe each of these individual parts also in a dCB format? In other words, what would be the control points of, say, this portion of the curve going from P0 all the way up to T0? How do you find the control points for that? And similarly, how do you find the control points for the rest of it, for the curve going from T0 to P4? And de Casteljau realized that there was a remarkably beautiful answer to this question, which in fact is sitting here in front of us. Now, if you become a member of the Wild Egg Maths channel, which I hope you all will, then you'll have access to not just all the videos in this and other series, but also I'll put out these worksheets and according PDFs, so you can follow along the lectures and actually make playing around with the various GeoGebra apps. All right, so let me remind you about the algebraic structure of these dCB curves. We're going to have a look in detail at this particular example. So this is something that I really encourage you to do, is to explore mathematics through careful and thorough analysis of explicit examples. Okay, this is a great way of proceeding. So we don't want to just be armchair theorists. We want to actually roll up our sleeves and make manipulations and calculations and explicit observations of things which actually really do exist that you can write down and study explicitly. Okay, so this is a great thing that we're doing. I hope you're sort of incorporating the idea of this is the way we can perform mathematics. Okay, so this particular curve, we know what the control points are. They're, in fact, just right here, okay, P0 to P4. So here is this general form for the curve expressed in terms of this parameter t. Okay, we saw that last time. So there are these polynomials, which are the Bernstein polynomials. These are the coefficients of P0, P1, P2, P3, and P4. These are polynomials in T. They're all of degree 4 in this case. Now, when you actually compute all of this out, then what you do is you get this curve, okay? The curve expressed as a pair of polynomials, or better yet, a pair of polynumbers. Okay, so these are degree 4 polynomials in T, and here they are explicitly. So the ingredients in here are these Bernstein polynomials. So let's just make sure that our notation for these is consistent. Okay, so we're talking sort of about the degree 4 Bernstein polynomials, and there are 5 of them going from index 0 up to 4. So this is B0, 4, this is B1, 4, this is B2, 4, this is B3, 4, and this is B4, 4. Okay. Notice that the binomial coefficients 1, 4, 6, 4, 1, which are the usual binomial coefficients associated with the number 4, are appearing here. Okay. Now, the general formula for these things is pretty easy to write down. So in general, for a general pair k and n, where k is between 0 and n, then this Bernstein polynomial b sub k comma n is this binomial coefficient n, choose k, and then there's a power of 1 minus t, maybe to the n minus k, and a power of t to the k. So for example, if k is equal to 3, then we get 1 minus t to the 4 minus 3, that's to the 1, and we get a t to the 3, and over here we're going to get 4 choose 3, which is 4. Okay, and so here again, then here's the curve. Let's call it gamma of t. And as t goes from 0 to 1, we trace out the curve from P0 up to P4. Now, as we stressed last time, there are really two kind of data objects here. And it's the relationship between these two things which is really important. So here's the relationship. So here are the 5 control points in order: P0, P1, P2, P3, P4. So that's a matrix that we formed, okay, which has 2 columns and 5 entries because there are 5 control points. This is the matrix of control points. And over here is the matrix which has down the columns the 2 polynomials thought of as polynumbers. So we like to think of a polynomial as rather a polynumber. It's a vertical list. So here's the first one: 4t, 6t squared minus 8t cubed, 4t to the 4th. And here's the second one: 8t minus 6t squared minus 16t cubed plus 15 to the 4th. So this is really a pair of polynumbers right beside each other. Okay, and the connection between these things is given by this. So what's going on here? So we're taking the matrix of coefficients, and here is that matrix Q that we talked about. It's like the inverse of the Pascal matrix P, which is just like this one, except there are no minus signs. And over here is a pleasant diagonal matrix with just the 4 level binomial coefficients down the diagonal: 1, 4, 6, 4, 1. And let's just check that. So if I select that and press evaluate, yes, it computes that. So that's good. Okay, so it's great to look at this specific example and to see the Bernstein polynomials. These are very attractive polynomials. Okay, and a lot of the properties of these curves ultimately comes down to properties of these Bernstein polynomials, which we're going to be looking at in more detail as we carry on. Okay, so now we want to look at what is de Casteljau's algorithm. So suppose that we're interested in the point that is actually appearing in our picture, this point right up here, when the parameter has value 0.4. We want to calculate what actually is that point. What are its coordinates? There's the control points. There is the point graphically. What are its coordinates? So one thing, of course, is to just use this formula. Okay, so we could use this formula. We could plug t equals 0.4 in here, and we can make this calculation. Okay, we could do that, but there's a little bit of complexity here because we're starting to raise this number, which is between 0 and 1, to relatively high powers. So if we were going to go, very small values of t, then we might end up with some round off errors or some problems here because of the relatively small nature of the numbers generated. So de Casteljau figured out that one could obtain such a point in a more indirect way using a certain algorithm. And the algorithm essentially goes through this geometry that you see here and it basically constructs all these points, in fact, in a very parallel way to what I've explained to you in my last video. So I want to go through that. So let's have a look at this. So let's set t equal 0.4. That's the point we're interested in. And suppose that we're interested in this kind of combination, okay? Because every single one of these segments that we're going to be looking at, we're going to go 0.4 of the way along. Okay, so it's going to be 0.4 is replacing t, so 0.6 times a plus 0.4 times b. We're going to be taking that combination over and over again. So to illustrate that, let's look at this. So first of all, let me just remind myself what definitions we have. Okay, I might actually, just to be clear, let me clear all the definitions so I can show you what's really going on. So, no, sorry. Let's clear the definitions. Clear definitions, all right. Okay, and now let me just make sure that we have these definitions. So in this kind of situation, I'm just going to select them all. And so let's check that I have, those are the 5 control points. All right, so great. We have those in our machine. And now what we're going to do is we're going to, we should also set t equal to 0.4. So let's set t equal to 0.4. So suppose I calculate this thing here now. 1 minus t p0 plus t p1. I can just evaluate that. I get 0.4, 0.8. Okay, so that was what we called Q0. So here's the result of that. It's Q0 is 0.4, 0.8. Now that's a very easy calculation. We know P0, we know P1, we know what T is. So we're taking 0.6 times P0 plus 0.4 times P1. Okay, and then if we wanted to go to the next Q, well, we just sort of bump up all these indices. Make that a 1 and make that a 2. And we're getting what we call Q1. Okay, if I go one more, I might actually do all of them. 2 and 3. We get Q2. And then from 3 to 4, that's the last one we can do, we get Q3, which is this one here. So this row, these are not actual equalities. These are just the results of the way I'm computing things. So I'm computing Q0 here first, and then Q1, and then Q2, and then Q3. So I've gone through all those segments involving the P's. Okay, so now what I can do is I can evaluate this. So I can set this equal to that, and I can set this equal to that. Okay, and I can set this equal to that, and this equal to that. Okay, and so now the Q's are registered. Let's just check that. There's the Q's. Okay, it's in a sort of a matrix form. I hope that's still going to work. We'll soon see. So now let's take corresponding combinations of the Q's. Great. So that's R0, right? That's that combination of Q0 and Q1. And then if I bump that up, I get evaluate. I get what we call R1, and then I bump that up again, and I get R2. Okay, so this row here is basically the calculation of R0, R1, and R2. Now I'm going to record these. Okay, save that one, and save that one. And now I'm going to go to the corresponding combinations of the R0s and R1s, for example. So this one here will then be 1.52. Oh, my battery's running low. Okay. This thing here that we just calculated is S0. And if I bump the indices up, 1 and 2, then I get S1. Okay, and I'm going to record these. And I'm going to record these. And then I'm going to use that with the same formula to get this thing here, and this is T0. Okay, so I want you to have a good look at what I've done here. So I've basically done the algebraic thing that I was doing in the GeoGebra app the other day. Okay, and we're proceeding one step at a time. So first with this P layer, and then the Q's, there's 4 of them, and then there's R's, there's 3 of them, and then there's the S's, there's 2 of them, and then the T's, there's 1 of them. And that's because we started with 5 control points. If we had started with 50 control points, well, then this whole process would be much bigger. This table would be bigger, but in principle, it would be exactly the same. It would have a triangular aspect. So, it has sort of a triangular shape because with each layer, the total number of new points is 1 less than the previous one. And finally, when we get down to just having a single entry in a column, and then we're finished, and that's sort of the most complicated point. That's the point that's then going to generate the dCB curve. So de Casteljau's algorithm is basically what I've just shown you. The Casteljau's algorithm is calculating all of these intermediate points explicitly just by repeated application of this linear calculation. Okay, so that's the point, that computationally this is really pleasant because at each stage we're only performing this linear calculation. In this case, 0.6 times something plus 0.4 times something else, and we're just repeating that. Okay, so this is the kind of thing that a computer can do very, very pleasantly. And it's also kind of numerically stable because you're just multiplying by 0.6, multiplying by 0.4, and adding. So let us actually check that what we're getting actually agrees with the other formula, the more sophisticated formula that we had, involving the points, only the points P0 up to P4, and these more sophisticated Bernstein polynomial coefficients. So eliminate that one. So we know what T is, we know what these points are. If I expand that, I get this, which agrees with this. Okay, so the de Casteljau algorithm is a kind of a one stage at a time, one linear step at a time replacement of this polynomial calculation. Okay, and if your arithmetic was not that great, you were reluctant about calculating higher powers of these things and doing all these calculations, then you might be quite happy with this systematic, relatively simple-minded way of proceeding. Great. Okay, and here's our picture again, just to remind us. So we've calculated all these points now. We have this table that has the entries of all of these points in a pleasant sort of triangular kind of array. Okay, so now we are able to utilize this to describe Paul de Casteljau's beautiful observation about what happens, which is really an expression of the miraculous nature of these curves. It really reinforces the idea that these are really interesting and lovely objects. Okay, so what we're interested in now is splitting this curve. Okay, so we want to split it right at t0 with this particular value of 0.4. Now, let me remind you why you might want to do that. Because if you are investigating some shape, right? I've told you that people who use these splines in applications, they want to apply the splines to relatively simple portions of the curve. So if you have some complicated curve, you first split it into manageable pieces and then create splines or dCB curves for each one of those individual pieces and try to make sure that they're aligned pleasantly at the places where they meet, typically by ensuring that their tangents are coinciding there. Okay, so an ingredient in that is taking a big dCB curve like this and splitting it and making it into two smaller dCB curves. And we want to describe, say, this first segment. We want to describe the dCB curve from P0 to T0. Okay, so it's the same curve, but not only a part of it. So we want T0 to be the new endpoint. Okay, so here is this beautiful thing that discovered by Paul de Casteljau. Okay, that the control points for this segment here, going from P0 to T0, are exactly these. The control points for this curve are P0, Q0, R0, S0, and T0. In other words, the control points are visible already on the diagram that we have already in front of us. It's exactly this little polygon. This one, this one, this one, this one, this one, essentially going through all of the colors. The first points in all of the colors. Okay, so how could we check that this is actually true? Well, so here is the formula for the a curve with given control points. But now instead of having P0, P1, P2, P3, and P4, I'm plugging in these ones. Okay, so here's P0, Q0, R0, S0, and T0. And let me just remind ourselves, do we have all of these points? Let's make sure that I have actually all. Oh, I've got all of them except for S0. I don't think I've got T0 yet. I think I may not have included that one. Let me go back up to here, make sure that this is also included in what our computer knows. So let me just check this now. Down to S1, S0, 2 R's, 3 R's, 4 Q's. Yeah, I think that's right. Okay, so our computer knows all these points. So now, if we look at this thing here, okay, let me just see what we get. So if we look at this, oh, okay, that's the value t. Sorry, I don't want t to be 0.4 anymore. I want t to be general. So let me put the cursor there and let me undefine t. Undefine t. Okay, so now t is variable, but the other points aren't. So let's see what this is. Okay, I'm going to simplify that. Okay, maybe expand it. All right, so this is a description of the, that's really the same as what's over here, isn't it? Yes, it's the same. Okay, so what is this? This is a description of the dCB curve from P0 to T0 with these 5 control points. We want to convince ourselves that that's actually the same thing as the original dCB curve that we were looking at. Okay, the original curve was this one here. Those are the P's and Q's that we've already found for the original curve. Okay, so if f of t is, say, the first one, maybe we should say p of t. I think that was more consistent with what we were doing before. So let's define p of t. And now if I look at p of 0.4 t, so I'm just sort of rescaling that. So you see this one here, this is 0 at 0, and it's 1 at the endpoint P4. But I want this to rescale it, so I'm going to put 0.4t here. And let me just see what we actually get here. You see, we're getting this thing here. And let me also look at Q of t being this one, the second one. Oh, sorry, this one. That's the second one of the original. Great. Okay, we'll make that definition here. And then we're going to evaluate Q of 0.4t. And we see we get exactly this thing here. So that's telling us that as in this thing here, as t goes from 0 to 1, that's the same as in this situation here of t going from 0 to 0.4. In other words, we're running right over that blue curve that we've already seen from the interval from p0 to t0. Okay, now that's for that part of the curve. What about the dCB curve from t0 to p4? Okay, so what's the story with the other half of the curve? We want to describe the dCB curve from t0 to p4. What do you reckon its control points are going to be? Well, I think you'll have not too much problem in trying to figure out what those things are, but I'll let you think about what that is and check that it actually works. Okay. So we've outlined de Casteljau's algorithm for, first of all, calculating a point on the curve. We've explained how to split the curve using de Casteljau's algorithm and to find the control points of a piece of the original dCB curve. Next time, we're going to have a look at this tangent kind of property and talk a little bit about tangency of dCB curves, connect with calculus that way.